Okay, so we're about 3 minutes after. I think we can go ahead and get started. People can keep joining as they have a chance. So welcome everybody to another IR Science Interest Group webinar. I'll be moderating the webinar today. For those of you who I haven't met previously, my name is Meredith McGregor. I'm an assistant professor at the University of Colorado Boulder, and I'm one of the co-chairs of the IR SIG along with Mike Zemkoff. Before I introduce our speaker, I want to go over a few instructions for how this webinar will work. I muted our speaker. I will fix that in a second. Give me 1 second. That fixed. You're good. Okay, great. What happens when I lock down the meeting. Okay, so a few instructions on how our webinar is going to work today. I typed these into the chat window so you can refer to them there, but just to say them out loud, please submit all of your questions via the chat window. If you don't have that up already, you can kind of mouse to the bottom of your Zoom window and click on chat, and that will bring up the chat window. So we're going to use that for typing in questions. You can type your questions in as they come up. There's absolutely no need to wait till the end of the talk. Once we do get to the end of the talk, we'll have a Q&A session, and then I can read questions out from the chat, but if you'd like to ask your question directly of the speaker, you can use the raise hand function to raise your hand, and then I'll unmute you and you can ask your question directly. For those of you who have not are not familiar with raise your hand in Zoom, or because they just recently relocated it, you can find it under the reactions button. So again, at the bottom of the Zoom window, there's a little smiley face that says reactions, and if you click on that, it gives you a bunch of options, and one of them is raise your hand. Okay. You can also use the chat window to submit any additional feedback or comments or questions you have for those of us on the Leadership Council of the IR SIG. We can try and answer those at the end if we have time, but we can also just send you an email response afterwards. You can report technical difficulties as well through the chat window. If something goes awry or you can't hear, please report those to the chat as well. And this webinar is recorded and will be available to view later on our website, and the link for the website is also in the chat window. I think that is all the logistics. So without further ado, I'll introduce our speaker for today. Today, Jed McKinney is giving us a talk. He is currently a fourth-year graduate student at UMass Amherst. Before that, he was an undergrad at Tufts, and he's going to be graduating in about a year and a half. So look for him on the job market soon. He's research interested in dusty galaxies at low and high redshift. And this past year, he participated in the IPAC Visiting Graduate Fellowship, or VGF program. Today, Jed is going to be talking to us about heating and cooling in the interstellar medium of dusty star-forming galaxies. And with that, Jed, I'll let you share your slides and take it away.
Great. Thanks so much for the introduction, Meredith. I really appreciate it. And I really appreciate the opportunity to talk to the IR SIG community. So to kick things off, everybody see my title slide okay?
Yep, it looks great.
Great, wonderful. So, right, as was previously introduced, I'll be talking to you all about heating and cooling in the interstellar medium of dusty star-forming galaxies. And I'll get into what that means, of course, throughout the talk, and provide some framework in the introduction. Of course, none of the work that I would be talking about would be possible without all my wonderful collaborators and advisors, in particular, Dr. Alexandra Pope, who's my thesis advisor at UMass, and also Dr. Lee Armis, who was my advisor for the Visiting Graduate Fellowship program via IPAC, which really launched a lot of the work that I'll be sharing today. There's a QR code up on the top left of your screen, which you can scan with a standard phone camera app. This will take you to the paper that we recently published that summarizes a lot of these results and goes into a little more detail, perhaps, as well. And then, of course, in front of you is this beautiful SED of the Circinus galaxy with various parts of the electromagnetic spectrum, specifically some important emission lines that correspond to heating and cooling, colored in red and blue respectively, that provide the observational underpinning for what my research tries to study in galaxies. Okay, So with that out of the way, I'm going to, oops, there we go. Just briefly outline what this talk will touch on. Of course, I'll provide a bit of introduction and background that goes into why we study dusty galaxies and what I mean by studying heating and cooling in the ISM of these galaxies. I will use this background to frame a discussion on the interstellar medium of local dusty galaxies. And then given what we learn in today's universe, frame some further discussion on what we can say about galaxies at higher redshift, and in particular, trends in galaxy evolution on the interstellar medium of these galaxies. Okay. So I like to start all my talks with this beautiful picture, which is of course the Hubble Deep Field, taken about 20 years ago, or 25 years ago, excuse me, which, you know, captured thousands of galaxies in this single long exposure and really revolutionized our understanding of star formation across cosmic time, revealing a rich history of star formation that extends far into the past history of the universe. And of course, there were many very high redshift galaxies in this early image that opened up the window into studying the high Z universe as well. Now, you know, I'm talking to the infrared community, so many of us may be well familiar with the fact that this is, of course, only half of the picture, and that nearly half of the star formation in the universe is obscured by dust. And so a few years later, when submillimeter and infrared maps of the Hubble Deep Field were being made, one of the great discoveries was that you have this population of unobscured star formation in galaxies, and then an equally important population of dust obscured star forming galaxies. And that together, these two detailed pictures of star formation in galaxies in both the UV and in the infrared tell an important history of star formation in the universe. And that is this familiar figure showing the rise and fall of the star formation rate density as a function of cosmic time. The left panel being the dust corrected star formation history based on UV observations, and then in the right, the star formation history of the universe as probed by the infrared. Both wavelengths, of course, find this important epoch in the history of star formation, that is the so-called cosmic noon, where more stars were being formed in the universe per unit volume than at any other time. It seems that star formation ramped up approaching cosmic noon, and then ever since, from a redshift about somewhere between 1 and 3 till today, that star formation has slowly declined on average. I really like this figure from Jorge Zavala's work in 2018. This is on the right. You can see again the star formation rate density as a function of redshift, now with both the UV and IR pictures superimposed on one another. A number of important qualities jump off of this figure. For one, most of the star formation at redshifts below 3, so in between about today and about redshift 3, most of that star formation is obscured by dust. Also, that obscured star formation is happening in heavily dust obscured environments, and in particular, some of the most luminous galaxies. And so that's what this top panel is showing, which is the fraction of the star formation rate density in the infrared regime that can be attributed to galaxies of progressively higher infrared luminosities. So around cosmic noon, much of the star formation happening in dusty galaxies is happening in these luminous infrared galaxies, or LIRGs and U-LIRGs. So all of this begs the question, why was there a cosmic noon? And we have a general understanding of the various physical factors that contributed to having a higher star formation rate density at around a redshift of 2. For one thing, simulations have helped us understand that preceding this epoch of enhanced star formation, the accretion of gas onto galaxies peaked. And that's what this figure on the left is showing, again, summarizing some results from simulation work. And this has been this is well informed because it supports this picture of enhanced molecular gas in galaxies as well, which is what the right panel is showing. And so we understand that more matter is being dumped onto these galaxies preceding the cosmic noon. And then at that time, galaxies also have higher reservoirs of molecular gas, which is of course the fuel for future generations of stars. So this is a sensible picture, but I think it's worth pointing out that in order to completely describe the star formation rate density evolution with redshift, something that's still hotly debated is whether or not galaxies need to have, on average, different star formation efficiency with redshift. So the star formation efficiency empirically is taken to be the ratio of the star formation rate in galaxies divided by their molecular gas reservoir. The inverse of this may be more familiar to some of you as the depletion timescale for star formation. In both cases, different authors come to very different conclusions, and that is that the star formation efficiency relative to its redshift 0 value in, say, a typical star-forming galaxy may be higher in the past by a significant margin, or perhaps not. So that is to say that redshift evolution and, say, the average star formation efficiency of a galaxy could be very important to understanding why we have a cosmic noon, or perhaps it is not. And so that's what this figure on the right is highlighting. I just grabbed some trends from various works published recently. So whether or not the star formation efficiency evolves systematically in these ways in redshift is still unknown, and it sort of depends on how you measure the molecular gas mass and the star formation rate. But we do know that more mass, that starburst galaxies, so galaxies forming an unusual amount of stars for their stellar mass, do exhibit higher star formation efficiencies, seemingly independent of redshift. And this begs the question, what can change the efficiency of star formation? And given that dusty galaxies are this really important population, particularly at cosmic noon, this is where I've focused my work over the past few years, building up to my thesis. So that is asking the question, what can change the efficiency of star formation in dusty galaxies on the level of interstellar gas in this population? So when you start studying the secular evolution of galaxies, of course, we run into a number of complicated and interwoven processes that ultimately determine the fate of a galaxy. And so these, of course, involve gas accretion from the intergalactic medium, star formation as gas cools from hotter phases into the cold molecular phase, then triggers star formation. These young hot stars can then interact with their environments, either mechanically through late stage stellar evolution processes like supernova, and then radiative feedback as well. And these can drive outflows in tandem with nuclear activity by a central supermassive black hole, all of which can shut down star formation as well. And so this complicated process ultimately determines the fate of star formation in galaxies. Now, there's you could draw lines between all of these as they're codependent in different ways. So just to focus my work, I've decided to focus on one key area of this picture, which is the star forming gas in these galaxies and the processes of heating and cooling within that star forming gas that go on to enable a future generation of star formation. Much of the neutral gas in galaxies that is cooling towards the molecular phase is locked up in photodissociation regions. And so well-known PDR, if you will, is shown on the left here. That's N42, the Orion Nebula, and you can see the Orion bar as well, this prototypical photodissociation region. And in these PDRs, gas cooling and gas heating compete with one another to determine the ultimate fate of this star-forming gas. So cooling is principally dominated through infrared fine structure lines at these temperatures, namely C+, O1, and silicon-2 emission. And the heating of gas, the radiative heating at least, is dominated by the photoelectric effect off of small dust grains or PAWs. And these can be observed in bright mid-infrared bands with, for example, Spitzer. So this figure of M42 is a great place to study the physics of photodissociation regions in stunning detail in the Milky Way. But galaxy integrated measurements of a lot of the tracers of heating and cooling that we observe in these Milky Way regions can be studied on galaxy integrated scales to infer the heating and cooling properties within the interstellar medium of extragalactic sources. And that's where my talk will eventually go, but I want to provide a little more background for the observables just to give people a handle on what I'm discussing later down the line. So I mentioned that most of the gas heating can be attributed to the role played by polycyclic aromatic hydrocarbons, or PAWs. These are small, effectively the small end of the dust grain population, small molecules consisting of carbonaceous rings. And through the photoelectric effect, after they absorb ultraviolet photons from hot young stars, those photoelectrons can go and share kinetic energy with their surrounding gas, thereby injecting heat into the gas. And so this is an important concept just to reiterate, because basically pH molecules mediate the coupling between stellar radiation fields and gas temperatures, at least in PDRs. So pH emission is bright in star-forming regions by consequence, because we can observe their vibrational modes as they relax after emitting photoelectrons. And so by extension, these emission lines are very bright in star-forming galaxies. And of course, Spitzer was great at measuring many of the spectra, both in local galaxies and at higher redshifts. As I mentioned, cooling in these PDRs is dominated by far infrared fine structure lines, more so in these dusty galaxies. And these are critical for enabling the gas cooling after PAWs have transferred energy from those stellar radiation fields into lifting the gas temperatures. So as I mentioned, most of this cooling comes in the form of C+, O1, and silicon plus at the characteristic temperatures of PDRs, and that's highlighted in this cooling curve on the right. So just to reiterate, these metal ions facilitate cooling to the molecular cloud stage. And as we could observe, PAW emission that's bright in these star-forming regions, and in particular PDRs, we can do the same as well with these far infrared lines, which tend to be co-spatial with the pH emission as well. So I'm trying to summarize this flow of energy from stars into the gas mediated by the heating and cooling. And I think it's helpful to invoke this cartoon, which does a good job in describing this process. So imagine a photodissociation region filled with PAWs, molecular and atomic hydrogen, and metal ions. You can see these PAW molecules are absorbing far UV photons, and via the photoelectric effect, heating the molecular and atomic hydrogen gas, which then goes on to collisionally excite these metal ions like C+, which can cool a significant amount of that gas through these far infrared fine structure lines. C+ is, of course, just one of them. I've mentioned a few already. And this also enables a set of observational handles on the flow of energy through these PDRs. In principle, we can measure signatures of the gas heating by studying these PAH vibrational emission lines in the mid-infrared, one example of which is shown in this bottom left figure in a Spitzer spectrum of a dusty star-forming galaxy, a local dusty star-forming galaxy. And other facilities are really great at mapping these far infrared lines, both in local galaxies made possible by Herschel spectra, and then in the Milky Way, it's also possible too. And then in high redshift galaxies, facilities like ALMA can measure these lines out to actually very high redshift. So these are powerful diagnostics of gas heating and cooling in galaxies, which can be combined to gain some physical insight on the flow of energy from stellar radiation fields into the gas temperatures. So I'm interested in studying these various emission lines to gain such insight into dusty galaxies, both today and at cosmic noon, to link the properties of heating and cooling with various aspects of star formation. So to understand the high redshift universe, of course, it's really important to have a firm understanding of what's happening in low redshift galaxies as an anchor point. And that was a large reason for why I began this project with Lee Armis, studying the GOLS galaxies, so GOLS being the Great Observatory's All-Sky Lurg Survey, a complete sample of infrared luminous galaxies in the local universe. And one of the really great aspects about the GOLS survey is that it spans a dynamic range in many important physical properties that we want to understand star formation along, and in particular contains a subset of galaxies that are pushed to some of the extreme conditions that are more typical of the galaxies that we're also studying at cosmic noon. And I'll show some examples of that later in my talk. I was able to do this project as part of the IPAC Visiting Graduate Fellowship Program, VGF for short. And if there are any students on the call, I certainly encourage people to check that out as a really great opportunity to pursue in a predoctoral career stage. In any case, that aside, a little bit more about the GOLS survey. This contains 202 systems, of which there are 244 galaxy nuclei. Many of these galaxies are mergers. These galaxies are high mass and about solar metallicity and above. And that's important because, of course, many of these cooling and heating processes are metallicity dependent. It's well known that the PAH mass fraction in the ISM is a strong function of metallicity. However, that seems to be more important at metallicities below the typical values found in GOLS galaxies. Something that's also very important for the purposes of this project is that GOLS has a really rich spectral coverage across the electromagnetic spectrum, which can be used to measure many properties of the ISM, including the ones I detailed previously. So the availability of Spitzer spectra gives us measurements of PA emission, as well as mid-infrared AGN fractions, and also opacities. And then Herschel observations can measure these far infrared cooling lines, from which we can derive all sorts of interesting things about the interstellar medium in these galaxies, including their average density, the strength of the radiation field that's impinging upon the surfaces of the average PDR, et cetera. And so on the right, I'm showing a Spitzer IRAC 8 micron map of one of the galaxies in the sample with some of the various apertures that were placed on these galaxies to extract the various spectra. And so you'll note there are subtle aperture differences between many of the instruments used to measure these various lines. And the paper goes into this in some more detail, but I was very careful about matching apertures and extracting consistent measurements in the various lines. So that naturally limited us to the smallest aperture, which in this case was the short low slit on Spitzer IRS. And so many of these results for the low redshift galaxies are specifically for the centers of these dusty star forming galaxies. Just wanted to mention that. So of course, all of these tracers have been well studied in GOLS and in other galaxies. And we've gained a lot of insight into the ISM from those works. So this figure is adapted from Tanio Diaz Santos's work in 2017, showing the so-called C+ deficit as a function of the infrared surface density. So this is simply the ratio of the C+ line to the total infrared luminosity in GOLS galaxies as a function of their infrared luminosity normalized by their IR size. And so something that came out of this study, and of course a lot of others, is that the brightest and most compact luminous infrared galaxies emit less power in cooling lines relative to their total effectively dust obscured star formation rate. And so this is problematic if you want to use some of these really bright far infrared lines to trace things like the dust obscured star formation rate linearly, because those don't scale with one another, as is evidenced by this figure. But it's important to note that the deficit that we're seeing in this figure on the left for the C+ line is also observed both in high redshift galaxies, for PAH emission, and for other cooling lines as well. So there's also some very interesting insight into the physical conditions of the ISM that you can gain from studying trends like this. Now, one might note that perhaps the total infrared luminosity isn't the most appropriate normalization factor for something like the C+ line. And what I mean by that is that the C+ emission is purportedly tracing mostly these PDR regions, thin envelopes around sites of recent star formation, whereas the total infrared luminosity contains a lot of dust emission from more diffuse gas across the galaxy, perhaps dusty gas that isn't locked in those PDRs. So there was a lot of early work to compare the strength of these cooling lines to the emission from PAWS that also is co-spatial with many of these cooling lines. And here's some work done by George Halou back in 2001. This is based on ESO observations, and showing the ratio of gas cooling through the C+ line to a photometric measure of the PA emission in some more normal star-forming galaxies as a function of the dust temperature along the x-axis. And what these early observations suggested is that the cooling to heating ratio is a constant in star-forming galaxies. And this is a really important result in my mind, because first off, this cooling to heating ratio helps define the flow of energy from the stars into the gas. So in some sense, it reflects our understanding of radiative feedback from hot young stars onto the surrounding gas temperatures in these galaxies. And so this can have important implications for how future generations of stars form as gas is cooling in these galaxies. So we wanted to ask whether or not this was the case when we looked at GOLS galaxies and pushed to some of the more extreme infrared surface densities. And so in the work that my recently published paper summarizes, we found that indeed, as you go to much higher surface densities, that the C2 over PA ratio actually declines in some of the more compact GOLS LERGs. So this is really striking because it suggests that the cooling to heating ratio in the PDRs of these progressively more compact galaxies is not constant, and that there's something changing in the regions of the ISM around these recently formed stars in such a way that the cooling in effect per unit heating declines. And that's what's sketched on this figure as well. And you can see where the GOLS trend sort of intersects, broadly speaking, with the Halou results as well. Now, of course, C+ is just one aspect of the cooling coming out of this PDR gas, and the GOLS sample has many observations of other really important cooling lines. And so I did a lot of work in combining all of the cooling traced by C+, O1, and silicon-2. And when you look at it relative to the total PAH emission, which again is tracing the photoelectric heating of gas, this is the trend that we recover as a function of the infrared surface density again in these galaxies. So just to walk through this figure a little bit, the y-axis is basically the cooling to heating ratio. The x-axis is the infrared surface density. The data that you're seeing are GOLS galaxies after strong AGN have been removed, because I would like to study the properties of star formation under the influence of basically stellar radiation fields. And in the top left, you can see that we've colored the various data points by this G/N ratio, which is the strength of the radiation field impinging on the surface of PDRs relative to their neutral hydrogen density. And what we find is that at higher infrared surface densities, the total cooling to heating ratio falls below the average of galaxies that are in more typical and less extreme conditions. And that this also happens with a an increase in the G/N ratio. So the energy density in these galaxies is larger, and the ISM conditions, if you will, are in effect more extreme, and that suppresses the total cooling to heating ratio. This y-axis is our attempt to empirically measure something called the photoelectric efficiency, which, if you haven't heard of this before, this is the fraction of energy absorbed by PAH greens that gets transferred into the gas. So in effect, we're seeing less cooling per unit PAH per less heating, because less energy, those PAH molecules are transferring less energy from the stellar radiation field into the gas temperature, which can then collisionally excite all these metal ions and then cool. So because we were trying to measure this, the so-called photoelectric efficiency, we can ask why it's low in some of these galaxies, particularly the more infrared dense galaxies with high G/N ratios. And when we do that, we find consistent results with both with theoretical understanding of PAH grains, which I'll summarize now. So this figure that just popped up on the right is, again, the cooling to heating ratio, a measure of the photoelectric efficiency, now as a function of G/N, previously the color bar. And you can see that there's an anti-correlation between these two quantities, as we expected, and that anti-correlation tracks well with various models of the photoelectric efficiency of PAH grains. And so these are PAH grains are great because they can be studied in laboratories on the ground, and also with modeling of how they behave. We have a good understanding for why they may have higher or lower heating efficiencies in effect. And so what we're seeing is that as you push to higher ratios of G/N, the models are telling us that the photoelectric efficiencies of PAH greens are falling, and that we recover that trend as well in our observations of Gold's galaxies. This also happens when gas temperatures are higher, and importantly, when the size distribution of the PAH grain population changes. And that's seen by the difference between these red and black curves. The red curve is emblematic of models that are more weighted towards smaller PAH grains, and the black curves correspond to models that have larger fractions of larger grains. So this is telling us that there's physics happening on the level of PAH grains in the PDRs of these galaxies that are changing in ways such that the net cooling to heating ratios in goals is declining in some of the most extreme conditions. And we can push even further to get some better understanding of why this is occurring through the lens of PAH grains, because many of these mid-infrared lines can be used to trace the properties of the grains themselves. So individual PAH emission lines trace the physical properties of the smaller grains, and in particular, trace things like the ionization state of PAHs and the average size of PAHs. It's well understood from lab experiments of PAHs and observations in extragalactic sources that both ionized and larger molecules have lower photoelectric efficiencies. In particular, ionized grains have lower photoelectric efficiencies because they have a higher Coulomb. Photoelectrons have to escape a larger Coulomb barrier, so they carry less energy into the ISM. And then the same can be said for larger grains on average. And you can see through this figure that the change in the ionization state of the grain has a strong change on various mid-infrared emission bands. And so the ratio of these bands can be used to infer to test for differences in things like the grain ionization and grain size. And this has been done quite a lot for both photodissociation regions of the Milky Way and galaxies by looking at Spitzer spectra, and in particular, the ratio of PAH lines detected therein. And so that's what these figures are showing for Goals galaxies, but as a function of the photoelectric efficiency. So the left panel is the photoelectric efficiency as a function of a measure of the grain neutrality. So moving towards higher values on the x-axis reach progressively more neutral grains on average. And this figure on the right is showing the photoelectric efficiency again, but now as a function of the average grain size. And so what immediately strikes me from looking at these is that there isn't a strong correlation between the photoelectric efficiency and the grain neutrality. There's actually a very weak anti-correlation between the photoelectric efficiency and the grain size measured through, in this particular case, the ratio of the 7:6 luminosity lines. And this is really interesting because for one thing, the central wavelength that a pH grain emits at is, broadly speaking, proportional to the size of the grain. So if you can study progressively larger separations in wavelength pH emission lines, then you have a better tracer, in effect, of the average grain size. So that is to say, the diagnostic utility of a pH grain size indicator can be proportional to the wavelength separation of the two lines that you're looking at. And a large subset of GOLS galaxies has observations from the Akari telescope, which gives us access to perhaps the most important pH size grain indicator, and that's the 3.3 micron emission line, which it turns out is really important. And that's what I'm showing in this figure here. So this is the photoelectric efficiency now as a function of the ratio of the 11:3 micron pH lines. So improving on the size diagnostic that I showed previously. And now when you fold in this 3 micron line, we find that there's actually a very significant anti-correlation between the photoelectric efficiency and the average size of grains. And this is, again, consistent with our theoretical understanding of pH grains, because as they grow in size, naturally their photoelectric efficiency is lower because they're larger, and any escaping photoelectrons both lose energy due to internal collisions with the grain, but also because of having to overcome a larger Coulomb barrier. Okay, and this is really exciting. For one thing, in our understanding of how the gas in these dusty galaxies today is cooling and heating, but also because the 3 micron line in particular can be measured out to very high redshifts, cosmic noon and beyond, by JWST. And so this might be a powerful diagnostic of heating and cooling in the ISM of galaxies at high redshift. But before I move into my discussion of higher redshift systems and bring all of this together and what it means for galaxy evolution, I just want to summarize the results of this local work into GOLS galaxies and sort of unify the picture of what we think is happening in the ISM conditions, both at lower and higher infrared surface densities. And I've attempted to sketch that in this cartoon here. So the image on the left is the typical PDR, if you will, in a galaxy at lower infrared surface density, perhaps more normal conditions. And then the PDR on the right is what we think might be more typical in a higher infrared surface density galaxy. So I'll work from the left first. These PDRs in more typical conditions exhibit in galaxies with lower infrared surface densities, have more normal radiation fields, if you will, and the PDRs are populated by a mixture of both large and small PAH grains, which dictate effectively the photoelectric efficiency, and we measure that to be on order of 8% or so. As you push to more extreme conditions, the strength of the radiation field cranks up, and you have a higher likelihood of observing younger PDRs, which are still in their natal birth clouds, perhaps. So these are dustier, more compact and young. In these scenarios, what we think is happening is that the strong radiation fields are in some manner reconfiguring the PAH grain size distribution mostly, such that small grains are less dominant in setting the photoelectric efficiency. So the larger grains are more important in terms of heating the gas. And so this corresponds to a lower observed photoelectric efficiency, which is why we see less cooling per unit heating when we compare these various tracers of cooling and heating. Okay, so in words, we find low cooling and heating ratios, the photoelectric efficiency at high infrared surface densities. and believe that these low photoelectric efficiencies arise because the radiation field strength is high, and that changes in some ways the properties of dust grains in the average PDR of these galaxies in a way that diminishes the transfer of energy from stellar photons into the ions. This, of course, being a form of radiative stellar feedback by stars into their surrounding environments. And I think this begs the really interesting question of whether or not such ISM conditions are also found in high redshift star-forming galaxies. And if they are or if they are not, how does that relate to our understanding of the higher star formation rates in cosmic noon galaxies? So both heating and cooling has been studied by observing PAH emission and cooling lines like C+ at higher redshift. Some of those results are summarized here. On the left, we see that the heating to total infrared luminosity as a function of infrared luminosity follows a similar deficit as observed in local galaxies at high redshift. So the high redshift galaxies in this case are some of the blue and red points. It's worth noting, however, that for a fixed value of LIR, many of these high redshift galaxies show more PAH emission per unit LIR. And so that perhaps is a first clue that maybe there's something different going on in the heating processes within the ISM of these higher redshift dusty galaxies. This figure on the right shows a lot of what we know about the cooling to infrared luminosity ratio as a function of LIR in high redshift systems. I think it's worth noting, however, that many of these observations are actually for galaxies at redshift 3 and above, even at redshifts above 6. And that's because in some cases, it's actually easier to observe like the C+ line, for instance, at redshifts above cosmic noon. So in that sense, our understanding of some of these critical cooling lines in cosmic noon galaxies is actually quite limited. And that's because basically the nature of atmospheric transmission at the ALMA site, which can go and measure from the ground many of these high redshift galaxies in lines like C+. So this is just a transmission curve as a function of the redshift that you would observe the C+ line at a given observed frequency. And so if you want to observe any galaxy in C+ at redshifts below 1, presently, the ground-based instrumentation doesn't exist for that, and the atmospheric transmission is exceedingly poor anyway. So that's going to have to wait until a large space-based telescope. ALMA's band 10 has opened up the redshift 1 to 1.4 window for observations with C+, but the transmission is admittedly poor. The same can be said for ALMA band 9, which gives us access to some of these key cooling lines at cosmic noon. But the transmission actually improves at higher redshifts. And so some of the lower frequency ALMA receivers are really great at getting lines like C+ at redshifts greater than, say, 3. And so that's why much of our understanding of these cooling lines in high redshift galaxies comes from studying galaxies at redshifts above cosmic noon. So this is something that I'm very interested in, and I wanted to change by effectively observing the C+ line in cosmic noon galaxies that also had PAH spectra to study the ratio of cooling and heating in dusty galaxies at cosmic noon. And so I'm going to briefly describe some of the observing strategy that we took towards observing these high redshift galaxies. First and foremost, we worked from a sample of Spitzer spectra of high redshift galaxies, some of which are shown in this right panel. I'm showing actually star-forming galaxies, one AGN spectra, and then a composite as well. But it's worth mentioning that the sample that I'm working with restricted itself to the star-forming galaxies. So those are those top panels. You can see many of the bright PAH emission lines in those as well. These galaxies are high mass and high metallicity. So along those axes, they're comparable to goals. And though the atmospheric transmission at the redshifted C+ line is sometimes poor, we can follow these up with ALMA and actually detect the C+ line. It would be great to measure things like O1 and nitrogen 2, the far infrared fine structure lines in these galaxies as well, but that's going to have to wait until a cryogenically cooled space telescope for us to observe them at high redshift. So this work has produced a Spitzer selected sample of redshift 2 LERGs with ALMA follow-up and also now VLA CO follow-up to link in the molecular gas properties of these galaxies. But here's a typical SED of a galaxy in our sample. And as you can see in pink, we have the PAH lines. We follow these galaxies up with ALMA to get C+, that's shown in red. The VLA results are shown in blue. And then in the inset panel, we also have spatially resolved information from the ALMA measurements of dust continuum in C+, and also HSD imaging. And this is really great because we can combine these various tracers to look at in detail the heating, cooling, and dense gas properties of these high redshift galaxies and compare them to all that we've learned about local systems. Something that immediately jumped out of this work, in particular from looking at the resolved sizes of these galaxies, is that the offset in the heating to infrared luminosity rate measured by the ratio of PA emission to total infrared emission that exists between redshift 2 and redshift 0 galaxies, that's summarized again on this left panel, that tends to disappear when you normalize the infrared luminosity by the size of the emitting galaxy. And so that's highlighted on the right, where for a fixed infrared surface density, the total heating properties of these LERGs perhaps aren't too different between redshift 0 and redshift 2. So that might resolve some discrepancies in their observations from the past. But the real strength of this work was in targeting the C+ line and being able to then compare the cooling and heating properties of these redshift 2 galaxies. And unfortunately, we were only able to detect the line in one system. We placed a robust upper limit on another out of an initial sample of 6 galaxies. But what we found is that, as shown in this figure on the right, the ratio of C+ cooling to PAH heating at higher infrared surface densities at high redshift tend to be below the values that are found in the local and compact LERGs. This one galaxy, GS-IRS 20, the square, where we detected the C+ line at really high signal to noise, could be consistent with the extrapolation of the trend found in local galaxies out to the more extreme infrared surface densities, but could also be below that trend in an interesting way. This could signal more cooling through higher critical density lines like the 001 line, which arises if on average, say your PDRs are more dense. Or it could be emblematic of low photoelectric efficiencies for the reasons pertaining to the properties of PAH grains that I discussed earlier. Again, you could have less cooling per unit heating because the dust grains, the pH grains, exhibit lower photoelectric efficiencies. And I think that's really interesting because it harkens back to the coupling between stellar radiation fields and gas temperatures in regions where cooling is very important for the formation of subsequent generations of stars. So the next steps are to try to more broadly understand the evolution in these ISM conditions over cosmic time, and in particular, answer the question, is there a link between the photoelectric efficiency and the efficiency of star formation? And is this something that evolves with redshift? So let's say the star formation efficiency is something that plays an important role in setting the high star formation rates of past galaxies. You may have a trend in the star formation efficiency as shown on this figure on the right, and I want to know whether or not the photoelectric efficiency follows that trend in evolution as well. Because the photoelectric efficiency being this ultimate mediator between radiative energy fields and the gas temperatures could have strong impacts for gas's ability to cool into the molecular phases. And this may then lead to what I'm calling efficiency-driven star formation at cosmic noon. And so there's ways to test this with CO observations of GOLS galaxies that we have to link the photoelectric efficiency and the star formation efficiency at redshift 0. And then I'm also currently working on obtaining both more C+ observations of high redshift galaxies to get a more statistical picture of what's happening around cosmic noon, but then also following up those same galaxies with observations of the molecular gas as well to make comparable measurements of low redshift dusty star forming galaxies and high redshift dusty star forming galaxies, and tease out the importance of things like the photoelectric efficiency on their star formation rates. So with that, it looks like I've been talking for about 45 minutes. I'd be happy to pause and take some questions and open this up for discussion. So thanks so much for listening.
Okay. Thanks, Jed. That was really excellent. You have some really beautiful graphics. I'm super impressed. So with that, then why don't we take some time now to have a Q&A session. So again, you can either raise your hand using the reactions button at the bottom of the Zoom window, or type questions directly into the chat window. Great. Okay, so Minhyun, let's unmute you. Hopefully, you should be able to unmute yourself.
Okay.
I'm in.
Hey, Jed, very nice talk. Good job. So I know, well, this is really interesting work and details are working out pretty nicely. But you know, I'm looking at really distant galaxies with high gas mass fraction, a lot of dust. And even for the local ULERGs with ALMA with high resolution, we begin to see the opacity becoming important, even in long wavelength. Yeah. And I think that will translate even more so to high redshift galaxies. So just I'm sure both at work, but just to take that extreme of these heating versus cooling having yet another component, which is basically shadowing. I mean, the ULERGs are not bright UV sources because there's a lot of crap in them, right? So sure. Can you draw a parallel to that and say what the impact of geometry and the dust extinction might be?
Right. I think so. Just to reiterate your question, you're asking about how are these measurements impacted by opacity measures that, in some of the more extreme cases, can extend to longer wavelengths than people typically think of in terms of extinction corrections in low redshift systems, right?
Right, because in the local universe, you don't find a lot of columns with exceeding 10 to 23, 10 to 24. It might be more common in an early universe.
Yeah, that's fair. So I think you know, on one hand, making careful measurements of these high redshift cooling lines and understanding the opacity effects at play will be important for when we make these larger statistical studies in the earlier universe. We can look at measures of the obscuring column from things like the 9.7 micron opacities in the Spitzer spectra, and we don't find a strong correlation between that and, say, the photoelectric efficiency in local galaxies. And it's right now the Spitzer data is a little noisy to make a similar claim for the high redshift systems. And of course, we only have 2 galaxies where we have these ALMA observations and the pause detected in the same system. But I think that would be one way to test the effects of the obscuring column from the availability of mid-infrared spectra as well. So of course, it would diminish the strength of the far infrared lines cooling relative to the PAH emission. So it's important in some sense to consider, certainly because that could in effect mimic some of the trends we're seeing as you crank up the infrared density, which is of course putting more, in your words, Min, you know, dust into a smaller region. And so yeah, whether or not it's playing a role in driving the conditions we're seeing in the extreme local galaxies, I think is unlikely, because there are trends with the O1 line, which we expect to be stronger when you start to really increase the PDR density, which would also increase the shielding. And those trends don't support the interpretation that the dip, it can solely be attributed to opacity effects alone, that you need more than opacity to explain some of the lower values we find relative to the PA heating, at least.
Great. There's two questions that have come up in the chat. So the first is from Ismail Garcia Burnett. He says, thanks, Jed, for this great talk. I would like to ask if the PA emission has been corrected by extinction. This can be quite important for the 11.3 to 3.3 PA ratio.
Yeah, excellent question. Thanks so much for bringing that up. So we have certainly corrected them for extinction, but the accuracy of those extinction corrections, of course, depend on the model that you feed in. A lot of these results are based on a subset of the goals sample that have been modeled with an updated version of the CAFE fitting code, which combines the mid-infrared modeling that was done on Spitzer and then extends the wavelength regime that's being done down to the 3 micron region with extensive modeling of the opacities as well. We were only able to run that on a small subset of the sample over the course of this project. Sorry, not small, about a third of the galaxies, as they were used in sort of a test case, and then inferred a correction on the 3 micron fluxes for the rest of the Akari data based on the more detailed opacity corrections obtained in those galaxies. It's worth pointing out that when we look at just the subsample, which we have these more accurate models for, that the anti-correlation we observe persists. And yeah, so we've done our best to make the extinction corrections on the 3 micron ratio that, as you've correctly raised, are really important in setting something like the 11/3 micron ratio. Thanks.
Okay. And another question from Phil Appleton says, how secure are your 6.2 micron PA fluxes at high Z? Yeah. It's hard to separate the PA from the continuum with the Spitzer spectra that you showed.
Yeah, absolutely. We specifically chose the 6.2 micron pH feature as like the anchor for measuring the pH emission in these galaxies because, right, as you've pointed out, those Spitzer spectra can be quite noisy. But because the 6.2 micron feature is the most isolated from, like, say, the 7, 8, and 11 lines, it is in some sense a cleaner line to measure. And we've done for the high redshift study, we did a fairly robust MCMC fitting analysis that hopefully captured much of that uncertainty in all of the data points that we plotted.
Yeah, I agree that you probably you can't be off by a factor of 100, which is what one of your points was, like 100 times below the normal ratio, right?
Right.
Yeah. So I agree that, yeah, I doubt if your uncertainties are that large, but okay, I'm glad you looked into that at least.
Okay, great. We're just about the top of the hour, but let's take one more question from Bernhard Schultz. How certain are you having excluded AGN contribution, which will make a continuum already at the PA wavelengths?
Right, so in the low redshift sample, we flagged out all of the GOLS galaxies that have really strong mid-infrared AGN indicators from high ionization lines, things like Neon 5 and O4. So we're fairly certain that we got some of those systems removed. We've also marked a lot of the data points on these figures, and this is in the paper in more detail, by the mid-infrared AGN fraction, which could be high in some systems that are really heavily obscured, and maybe we missed them in our original flagging scheme because some of those really strong ionization lines themselves were attenuated very extremely. And so I think so I'm making the caveat here that when we look at only the pure star forming component of galaxies, so the subset of GOLS galaxies that were, through modeling the continuum and looking at the high ionization lines or lack thereof, we're very certain that there isn't a very strong AGN, that when we only look at that subset, the trend that I've described over the course of this talk of having low photoelectric efficiencies in the more infrared compact galaxies, that persists when we try to make an even more stringent cut on the AGN population. The high redshift, of course, the case is noisier in high redshift galaxies. The Spitzer spectra are noisier, and we're restricted to only using one pH line when we're looking at the properties of the cooling to heating. But we do a full Bayesian model of the continuum and the PA lines as well. This decomposition method has been shown to work well for high redshift galaxies when you look at other tracers of the AGN activity too. So we've done our best to exclude AGN from the measurements, in both low and high redshift scenarios.
Oh, thanks a lot.
Thank you.
Okay, great. So lots of comments saying how great a talk it was. So let's thank Jed again for a really excellent talk. And I'll just thank all of you for joining us and remind you that we have these webinars on the first Tuesday of every month. Same time, always 1 p.m. Eastern. So please do join us for future webinars. If you would like to give a webinar yourself, reach out to me or one of us on Leadership Council, or if you'd like to suggest a speaker, please do that. We're especially excited to get early career scientists from diverse backgrounds. So have a great rest of your Tuesday, and thanks for joining us, everybody.
Bye. Thank you.
Thank you, everybody.